everyone. We hope you are enjoying the enriching sessions of this faculty development program on quantum computing. It's been an exciting journey so far, diving into the depths of quantum computing and its applications in various domains. Welcome to the session 5 of day 3, where we will take a hands on approach to explore quantum computing through this topic. Practical training on quantum simulator QSKit. This session promises to be an engaging and practical experience as we learn how to implement quantum algorithms. Our esteemed speaker for the session is Dr. Jayakumar. Vetya Shankar is the founder and CEO of Anunthara Private Limited. He also serves as an IBM quantum educator and an IBM QSKit advocate mentor. He is actively building a quantum community in India and is an IBM certified associate developer in quantum computation using QSKit. With 15 years of experience in R&D and university level lecturing, he is a senior IEEE member actively participating in IEEE quantum standards. To date, he has published over 15 research papers in international peer-reviewed journals and conferences. Additionally, he has been appointed as a technical paper reviewer for IEEE quantum conferences. He is also a Swayam NPTEL portal instructor for the All India Council for Technical Education, which is AICTE, and the Department of Science and Technology, DST, which launched India's first undergraduate minor program in quantum technologies. Dr. Jayakumar has conducted over 300 quantum programs, including faculty development programs, QSKIT certification training, and awareness camps across India, Nepal, USA, Russia, Armenia, Poland, and Malaysia. In this session, Dr. Vaithya Shankar will guide us through the fundamentals of QSKIT, demonstrate practical implementations, and provide insights into how quantum simulators can bridge the gap between theoretical concepts and the real world applications. Before we proceed, a quick reminder to all, please keep your microphones muted during the session to ensure a smooth experience for everyone. If you have any questions, feel free to drop them in the chat box and we will address them during the Q&A session at the end. Without further delay, let's give a warm welcome to Dr. Jayakumar Shankar as he takes us through the hands-on training on QSKit. Over to you, Dr. Jayakumar, sir.
Thank you, ma'am.
Welcome,
Thank
sir.
you so much. Thank you. So, good evening to all. So, we will start our session. Let me share my screen. I hope my screen is visible to you.
Yes, sir.
Yes, sir.
Okay. So, I am Jayakumar. Let me minimize this. So, I am acting as an IBM quantum educator for past 6 years. So, if you are interested in quantum learning, so please go through IBM quantum challenges. So, Okay. Okay. So if you're able to complete these challenges, they will give digital badge and certification to these challenges. So apart from challenge, you can look for summer school. So summer school contains 2 weeks program. So all these two are conducted through online. Okay. So they will conduct for 2 weeks. So you need to enroll beforehand. It is starting so much of competitiveness for this summer school. So once you completed summer school, you can look for certification. So certification cost 10,000 rupees. So whatever I show in this slide, only the certification cost 10,000 rupees, remaining everything free of cost. So if you go through the certification, you'll get lot of idea. I'll share that link to you. So I'll share in the chat box. In meanwhile, you can go and check. Check whether it is loading. It is not loading for me. Hello, is it loading? Please put in the chat box. Okay, fine. Maybe server busy. It will take some time. Yeah, taking long time. Okay, no issue. I'll go with my slides. So once you completed certification, you can look for advocate post. So you can be a part for core team. Okay. So once you completed advocate, you can look for 3 months internship. So once you completed internship, you can go for mentorship. So this is the career path in IBM Quantum. So you can choose according to your level. Apart from this, you can complete so much several free IBM Quantum courses. So these are the free IBM Quantum courses. I'll share this link with you. I'll share this link with you. I hope this website loading quick faster. So go here, click Learning tab, view all courses. So side by side, I'll share this link. So you can look basics of quantum information, first course. So go to this course. So you can see so many modules, single system, multiple system, quantum circuits, entanglement in action. Okay, it contains 4 modules. So click lesson 1, introduction. You can find YouTube video. So this course is taught by Professor John Waters. Okay, so you can watch this video. So this will go for 1 hour or 1.5 hours. So most of the people not able to understand everything in a single shot. So you need to watch multiple times. So if you have any doubt while watching this video, you need to pause. You need to go to Google, ChatGPT. You need to go for reference. Then you need to come back to video. So if you want to study quantum computing, you need to pause and you need to refresh. Then you need to come back. So you cannot learn quantum in a very linear way. So it is a non-linear, right? So the second option, you can download these slides from this link. Okay. Otherwise, what you can do, you can right click this page and you can take print. So this will create a PDF. Okay, take printout, then read. Because if you go further, you will have lot of mathematics. So reading in online you will get tired easily. Okay. So finally, if you go for Qiskit implementation, so it consists Python code. So you can run Python code then and there itself, or you can use Google Colab. So multiple ways you can learn this course. Okay. So this is the first course I'm recommending each and every one of you. Automatically it is drawing. How to erase? Okay, fine. So if you come down, you can have exam. This course contains 20 questions. You need to answer 16 correctly. If you're able to clear this exam, you will get digital badge and certification from IBM free of cost. Okay, fine. You are sharing this link. Thanks. Once you completed basics of quantum information, you can go for fundamentals of quantum algorithm. Then you can proceed for any other course. So most of you want to learn quantum machine learning. So before learning quantum machine learning, so it is advisable to complete course 1 and course 2. Without course 1 and course 2, you cannot understand quantum machine learning. So this is the basic criteria. Suppose if you are from management side, okay, MBA side, if your friends working in MBA side, you can recommend Quantum Business Foundation for them. If you are involved in quantum cryptography, you can go for practical introduction to quantum safe cryptography. So all these courses have digital batch, and also you will get IBM certification free of cost. So this is about this slide. This is about this slide. So this is how quantum computer will look like. Okay, so quantum computer is made up of superconducting materials. So whichever material has superconducting property, you can use those material to construct this machine. Okay, so this machine is made up of gold, copper, mercury, whichever is superconducting material. So you are able to use it. So each and every layer you can see over this diagram, it will reduce the temperature. It will reduce the temperature. Okay. So you can see so much of wires which will conduct microwave pulses. So quantum processor will be there. Quantum processor will be there. Okay. All your computation are get done over here. Okay. So inside this quantum computer, the temperature will go minus 273 degrees Celsius, near absolute zero. So you can see the red color shield over here. So this will cover the entire quantum computer. So I'll show in this next slide. So this is how quantum computer covered by using the shield. So they are using the same technology in rocket cryogenic engine. Okay. So inside this computer, the temperature will go minus 273 degrees Celsius. So this is how a real quantum computer will look like. And this is one architecture. This is one architecture you can focus. And this is about investment across the globe. So US invested $1.2 billion, India invested $1 billion, and China invested $15 billion. So investment of India need to be higher. So $1 billion is not sufficient to become a leader. So in future, they will increase, I hope so. So this is one good organization, qubit by qubit. Suppose if you want to make your children to learn quantum, this is very good platform. This is an NGO. They are providing quantum education in US from 8th standard. From school 8th standard, they are offering this course. Okay. So look at the sponsor, IBM Quantum, Google Quantum, Microsoft, Unitary Fund, everything is involved. So NSF, National Science Foundation, they also involved in this trend. Okay. So look at this website, qubit by qubit, helpful for you. So this is American government National Quantum Initiative. So they prepared some strategy to become a world leader in quantum domain. So based upon this, India also developed National Quantum Mission. So in April 2023, they allocated 6,000 crores. Okay. So very important mission for India. So within 2030, we aim to create 10,000 1,000 physical qubits. So this is our ambition. So for this mission, we have four important pillars: quantum computing, quantum communication, quantum sensing and metrology, quantum materials and devices. So we have four hubs. We have four hubs. So each hub contains so many technical groups, so many teams, so many lead members. So it contains a geographical location. This map contains geographical location. So IIT Delhi responsible for quantum materials. IIT Bombay responsible for quantum sensing. IIC Bangalore responsible for quantum computing. IIT Madras for quantum communication. So I'll share this material in your free time. Please look at the resource available within your geographical area. Try to visit this campus. Before and you need to get permission from authorities. And this is the good news. Before 4 months, state government of Andhra did a MOU with IBM, TCS, and L&T. They are about to set up a quantum valley in their new capital, Amaravati. So for this, they allocated 4,000 crores. They purchased IBM quantum system for this. And this is one facility I visited in ISER Pune. This facility is about nuclear magnetic resonance. So this is the infrastructure they have. So whatever you are observing in this diagram, it look like a Jane magnet. Okay, Jane magnet. And this will help to do quantum computation. Okay, so this magnet is 10,000 times powerful than Earth's magnetic field. So this is one more facility in IISc Bengaluru using quantum optics. So this is a tabletop model. This small space cost 3 crores. The time taken for set up this lab took 3 years. So by millimeter, they need to calibrate this lab. And this is one more lab in IISc Bengaluru, cryogenic quantum lab. Okay. So whatever you see over here, you please go through all these links. You will get some idea. Okay. So whatever you see over here, here you have quantum processor. Here you have quantum processor. So this is built by engineers. So this is built by IIC team. So you can observe the background components. Background components. Okay. So all these components are imported from UK. Okay. Only the processor built in India. Our aim is to build all these components. So this is one more facility in ISER Bhopal in Madhya Pradesh. Okay, they use diamond, NV diamond, nitrogen vacancy in diamond. So diamond has some nitrogen vacancy. It will act like impurities. Okay, so these impurities will help you to do computation. So each and every quantum computer have different architecture. Each and every quantum computer have different architecture, and you will be used for different purpose. And this is about NPTEL workshop, quantum workshop, happened at ISER Bhopal. So I participated 1 week workshop. So please note down this institute, ISER Bhopal. They will conduct 1 week workshop offline. So this is one facility available in IIT Kanpur. So using quantum optics and entanglement lab. So these are their facility. They invited for recording NPTEL Swayam course. I stayed for 1 month. We recorded nearly 13 courses. So they're about to launch in NPTEL website. So this is the national initiative taken by 3 IIT and 4 NIT. So QT series. So they ran almost 8 series. So our team contributed for this workshop. Most of you, I hope so, are participant. And this is Q Karyashala. This is Q Karyashala, right? Happening in online, happening in offline, IAC Bengaluru. So each and every year, uh, third week or fourth week of June, they will conduct 2 weeks workshop. And Indian government, DST along with AICT want to create workforce in quantum. They introduced undergraduate courses. Okay, a minor degree in quantum. So this is the curriculum they built. If you go to AICT, if you search for quantum technology, you will get this curriculum. So if you have time, if you are planning to implement minor degree in your institute, please go through this curriculum and you will have a broad idea. And these are the courses they planned. So there are totally 11 courses. Out of 11, if any faculty attended 6 FDP, they will get PG diploma from AICT. If any student able to complete 6 courses from NPTEL, they will get minor degree in quantum. So this is about our startup, Anutandra. So Anu means subatomic level, Tandra means technique. So we are dealing with quantum technology. So that is why we aptly named Anutandra. This is about our team. I'll share this material to you. And today we're going to discuss about IBM Quantum Platform. So it will help you to do simulation and also real-time execution in a quantum system. So each and every month, so I will take my pen over here. Each and every month, they will give 10 minutes access to real-time quantum system. So normally they will charge 9,000 rupees per minute. So 10 minutes means nearly 90,000 rupees they will charge, but they are providing free of cost. Okay, 10 minutes you can use a real-time system to do your computation. So this is very good platform. Okay, to create this platform, you need to have credit card. So all of you go to IBM Quantum platform, go to this link. So please attend with the help of laptop or CPU. Don't watch using your mobile. You cannot do. Every architecture is based upon which quantum material you are using, quantum element you are using, particle you are using. According to that, architecture will vary, application will vary. Yes. So go to this platform, click top left, come to composer, come to composer. All of you able to go to this link. I'll share this link in chat box. All of you able to go? It is loading. No need to sign. No need to sign. So without login also you able to use this tool. So if you are not able to access your system, don't worry. Watch this video, they will share with you. So after some point of time, you can do. Don't worry. So without login also you're able to use. So click here, Q0, select bin button. Click Q0, select bin button. Click Q0, select bin button. Click C4, select minus. Click C3, select minus. Click C2, select minus. So we have one quantum bit, one classical bit. So Q0 stands for quantum bit. Okay. C stands for classical bit. So try to follow. If you are not able to follow, don't worry. This video recording will be available. So after session, they will share with you. Okay. I hope all of you able to access. Okay. So without login, you can do. Okay. For understanding, I will tell how to log in. So you need to have credit card. So using credit card, you're able to log in. So be aware, they will charge. So be cautious when you create an account. So I logged in. So you can see my details over there. So likewise, you can have some profile over here once you logged in. So without login also, you're able to use this tool. Don't worry. So to understand qubit, we need to start from block sphere. We need to understand from block sphere. So block sphere, it is a sphere, three-dimensional, it could be two-dimensional. The radius equal to 1. Radius equal to 1 means it is a unit sphere. Okay, so unit sphere divided into two halves. Okay, so this equator will divide your block sphere into two hemisphere because we need to represent two level system. We try to replicate binary system. Okay, so we have binary data, so that is why we are using qubit in terms of two divisions. So as usual, we have three axes, x, y, z, and we have two extreme points, polar points. Okay, so this point is, I try to take highlighter. So this point is extreme for North Pole. This point is extreme for South Pole. Southern Hemisphere. Sorry, Southern Hemisphere. And what we are doing, we try to map our physical data into the qubit. So this is a block sphere, a visualization of a qubit, quantum bit. Okay, so we have binary data 0, binary data 1. We are mapping as state 0, state 1 in pure states. In pure states. So these polar points are called pure states. So this is very, very fundamental in quantum. So we are converting binary data into qubit. So we are associating value 0 to North Pole, value 1 to South Pole. In quantum, you need to say quantum state, 0 state, state 1. So after this, we are taking a random location in the Bloch sphere. Okay. So imagine this is your location of an electron, photon, ion, any subatomic particle, a single subatomic particle. Okay. So from this point, we are generating an vector. So this navy blue vector is called quantum state vector. So note down these things. So if you have pen and paper, please note down. So this navy blue is called quantum state vector. So this quantum state vector will give information about your quantum particle. Information about quantum particle. Okay. So from this point, we try to explain mixed state. So it is not in state 0. It is not in state 1. It is the mixed state between state 0 and 1. So like superposition. Quantum state vector contains complex numbers. It contains positive, it contains negative, it contains complex values also. So we'll discuss, wait for some time, we will discuss. So from that point, we try to slice the sphere. We try to slice that sphere. So this is xy dash plane, x dash and y dash plane, axillary plane. So from this point, what we are doing, we try to do a projection. We try to do projection. Okay. Projection to xy plane. Projection to xy plane. It will do intersection. It will do intersection. Okay, in xy plane. From this intersection, you are doing one more projection towards origin. Towards origin. So if you have pen and paper, please draw this diagram and note down these notes. It will help you. So what we had, I will revise. So we have a Bloch sphere. We have a Bloch sphere. So we are dividing the sphere into two hemispheres, and we are taking three axes, and we are mapping our real binary data to qubit. We are choosing polar points, and these are called pure states. So these are known state for user. Okay, so from this, we are taking an arbitrary point. So this green dot, from this green dot, we try to generate a vector from origin. So this vector act like a quantum state vector. This will give information about your quantum particle. So if you do any quantum gate operation, this will get changed. This location will get changed accordingly. Okay, so this is a mixed state. So it is not a pure state. So all these points in this sphere are called mixed state apart from your North Pole and South Pole. Okay, so from this point, we try to create x dash and y dash plane. From from this point, we try to do a downside projection. So it will have intersection with xy plane. From this intersection, we try to do a downside projection towards origin. So it will create a right angle triangle. So it will create a right angle triangle. So once you got a right angle triangle, once you got a right angle triangle, you can apply trigonometry. So that is the purpose we are doing all this stuff. So taking notes. So once you have right angle triangle, you can apply trigonometry. So trigonometry involving with angles. So it will create angle between your z-axis to your quantum state vector, which is called theta. So this is the first angle. Similarly, it will generate one more angle between your x-axis to downside projection, which is called psi. Say we got two angles. So what is our intention? We try to convert xyz, xyz, okay, Cartesian coordinates into polar form, into polar form, theta and psi. So this is the reason. So recall this point. So recall this. So between your z-axis and your quantum state vector, it will create an angle called theta. Okay. If theta equal to zero, if theta equal to zero, this quantum state vector will point to z-axis. It means this green dot will come to your z-axis. So this is the first case. This is the first case. So theta equal to zero. This is your quantum equation. So this is called wave equation. Okay. So this is your quantum particle. This is your quantum particle. Quantum particle. So normally it is in superposition. Normally it is in superposition. Okay. It contains state 0, state 1. We are adding quantum states. We are adding all quantum states, all quantum states to define superposition. So this is the primary purpose. That is why we are adding. So this is a linear combination. So technically what we'll call it is a linear combination of all quantum states. Okay. So we chose cos theta and sin theta. Okay. So cos and sin are opposite in nature. So if you go back and refresh trigonometry, cos and sin will represent opposite nature. So you can associate cos with pure white, you can associate sin with pure black. So if you want to represent any opposite components, signs or signals, okay, you can associate with sin and cos. So apply d equal to 0. What is the answer you will get? Put in the chat box. Get 0. Exactly. So any other answer? Okay. So most of you got get 0. Very good. So this whole component become 1. This whole component become 1. So 1 into state 0 plus this whole component becomes 0. So 0 into state 1. State 1 will get 0. So finally you'll get state 0. Finally you'll get state 0. So this is an example for identity gate. So if you apply d equal to 0, the quantum state will remain the same place, same location. Exactly. Very good. Very good. So all of you able to follow? I hope so. Now what we are doing, we try to implement d equal to pi. We try to implement d equal to pi. Okay, applying this formula and tell me what you will get. I will explain. I will explain. I will explain why deta pi by 2. I will explain. Yes, yes. It is a logical abstract concept. So any quantum particle you are able to represent. Very good. You need to mention state 1. So you cannot mention just one. So it is a state 1. So this is a state 1. Okay. The sign cos part becomes 0. The sign part become 1. So 1 into state 1, you will get state 1. So this is mathematical description. But if you look geometrically, okay, visually, it will go from state 0 to state 1. So in this way. So one more time I will show. Now we are in state 0. If you apply d equal to pi, it will go a full swing, pi rotation. It will come to state 1. So this is equivalent to your NOT gate. This is equivalent to your classical NOT gate. So classical NOT gate, what we'll do? We'll give 0, we'll get 1. If you are giving 1, you'll get 0. So the same thing will happen. From state 0, if you apply NOT gate, it will come to state 1. From state 1, one more time, if you apply NOT gate, it will go back to state 0. Yes, very good, very good. So maximum value of data, it can give 2 pi. It will come to the same place, right? So if you give 2 pi, it will come to the same place, the whole circle of that sphere, whole rotation of that sphere. Very good, sir. Very good. So much of interesting question from this session. I really appreciate. So people are engaging, they are watching, listening after evening also. Very good. So do this. If you apply d equal to pi by 2, then what happens? Put in chat box. If you apply d equal to pi by 2. So we discussed d equal to 0. D equal to 0 means it will look like identity gate. Okay. Then we apply d equal to pi, it will appear like a NOT gate. If you apply d equal to pi by 2, what it means? Yeah, maximum value 2 pi, right? So beyond that, you cannot have any value. It is like a rotation. Exactly. So this is a Hadamard gate. This is technically called Hadamard gate. If you apply d equal to pi by 2. So otherwise you can say it is half NOT gate. It is half NOT gate. So you can say square root NOT. Square root NOT. So it will move your quantum particle from state 0 to x-axis. So you can look at here. So it will transform from this place to this place. So what is the location? Location exists in equator. Location exists in equator. It means it is 50% away from state 0. Also 50% away from state 1. So this is an example for Hadamard gate, very important gate in quantum. So note down Hadamard gate. It will create Equal superposition. Equal superposition. Exactly. Okay. So next, we try to cover second angle. So look at here. So we are focusing on psi equal to pi by 2. If you are operating psi, then you will get imaginary component. Imaginary component involved within your equation. So x-axis contains real components. So x-axis contain real components. Okay, so note down this difference. In case of y-axis, it contains imaginary component. Okay, so always imaginary component associated with state 1. So you can notice over here. So imaginary component reacted with state 1. And you can notice a strange thing. So stage 0 will get, sorry, d equal to 0 will get stage 0. D equal to pi will get state 1. Okay, so d equal to pi by 2, we have the common terminology called 1 over root 2. 1 over root 2 multiplied with stage 0 plus state 1. Anybody can tell what is the meaning of 1 over root 2? Why we got 1 over root 2? Put in the chat box. Can you figure out why it is coming 1 over root 2? Probability. Okay. Any other answer? So look at the block sphere. Look at the block sphere. You will have some idea. So we are dealing with cos and sine. So when you will get 1 over root 2 value, 45 degree. Exactly. Exactly. Very good. Very good observation. Okay. So sine 45, cos 45, you will have value 1 over root 2. Very good observation. So that is fine. So if you apply d equal to pi, psi equal to pi by 2, this imaginary component got activated and you will have imaginary component related to state 1. It means you will have shift, okay, phase shift from x-axis to imaginary axis y. Okay, so this is a phase gate. This is a phase gate. What is the value? Pi by 2. So note down all this stuff. We covered z-axis. Z-axis contains state 0, state 1. How to hide slide control. Okay. So we covered z-axis. Z-axis contains state 0, state 1. X-axis contain positive state and negative state. So positive axis, positive state. Okay. Negative axis, negative state. In short form, we are calling. Similarly, y-axis represented with plus side and minus side. So that is why a quantum state is in the form of complex number. So complex number will have positive value, negative value, and also imaginary component. So if you have three pairs, okay, you can represent a quantum particle anywhere in your Bloch sphere. Anywhere in your Bloch sphere. So this is stage zero. This is stage zero. We are representing in the matrix form. Okay. So this is stage zero. We are representing in the matrix form. So what we are representing? We are representing quantum state. Okay. So quantum state we are representing in two hemisphere. This is northern hemisphere. This is southern hemisphere. Okay. Imagine like this. Okay. So consider stage zero. Stage zero located in northern hemisphere. So look at here, stage zero located in northern hemisphere. That is why you put 1 for the upper component, 0 for lower component. Okay. So if you want to realize the physical meaning of a matrix, quantum will help you. Okay. So most of the time we are doing abstraction in mathematics and matrix. We don't know why we are representing that format. Okay. So everything have physical meaning, originated from physical things. So that is why the upper component is 1 for stage 0. The lower component is 0 for stage 0. Because it is nothing to do with southern hemisphere. Okay. So what is the format for state 1? Try to put in chat box. Exactly. So 0, 1. So you can put in this way. You can put in this way. 0 alt enter 1. So always you need to maintain this column format. Okay, column matrix. Everything is physical. Once you understand physical, you can use mathematics in such a beautiful way. So this is for state 1. So state 1, nothing to do with northern hemisphere, dealing with southern hemisphere. So we are representing its presence. Exactly. Okay. So how will you represent positive state? Can anybody tell how will you represent positive state? Yeah, we'll cover the basic quantum gates. We'll go for composer. So we need to have strong theory, then only we able to use the tool. Can anybody put chat box? Exactly. But in the form of matrix, definitely they are recording. You will get this recording. Think in the terms of the same format, stage 0, state 1. Your answer is partially correct, fully correct, but not in this format. Okay, exactly. So you can represent in this way. So positive state both related to northern hemisphere, southern hemisphere. Okay. So what is the ratio? 1 over root 2. This is the common term. So you can represent in multiple ways. But if you look this format, it is easy to grab idea. Okay. So for negative state, it is opposite side of the sphere. So this is opposite side of the sphere. That is why the second component, you got negative side. So always imaginary, right? And sign change will happen at state 1, not at 0. So note down this point. Always imaginary and sign change will happen in state 1, not in state 0. Okay. So how will you represent for positive I? Put in chat box. If you understand this, you can understand positive I. So the second component become I. Simple. The second component become I. Okay. For negative I, the second component become minus I. So you can find similarity between all these quantum states. You can find similarity between all these quantum states. Very good. Very good. So finally, you can visualize your Q sphere, okay, block sphere in the form of matrix in this way. Yes, sir. We'll start. We'll start. So go to this link, block sphere. So it will help them to understand composer in much better way. See, for positive, you look at the position, location. For positive, you look at the location, where it is located in between northern hemisphere and southern hemisphere. That is why both components are there. So if you understand 0, you're able to understand state 1. If you're able to understand these both, you're able to understand positive. Okay? Are you able to understand now? Okay. For negative, it is in opposite side of the sphere. It is opposite side of the sphere. This opposite side, you are denoting with negative sign. You are denoting with negative sign. I hope you are able to understand. If you are not able to understand, don't worry. You watch the video. Watch this video. So once we have the clear idea about all these concepts, then we can go for Quiskit composer. So don't worry about that composer. So go to this link. Go to this link. Okay. So I will try to quickly explain all these logics. Right. So we have two states, pure states. So let me take my pen. Okay, pen is here. So these two are pure states. These two are pure states. So if you are preparing qubit, either you can prepare from 0 or either from 1. All these are binary value. All these are binary value. Okay, so we converted binary value into quantum states. So that is why these are known value for users. Known value for users. Okay, so I'll discuss classical NOT gate. So this is NOT gate, X gate is NOT gate, X gate is NOT gate. Okay, so we are in stage zero. We are in stage zero. So look at here, your quantum particle in north pole. So if you apply NOT gate, it will go to state 1. If you apply NOT gate, it will go to state 1. So click X, observe down. So it will went to state 1. It will went to state 1. So that is what I denoted. From state 1, again if we are applying X gate, it will go back to state 0. So I am in state 1. So look at here. If I am again clicking X, it will go back to state 0. So this is classical NOT gate. All of us know. All of us know. The second one is Y gate. So Y gate is quantum gate. So X gate is not quantum gate. Okay, but Y gate is quantum gate, which will do NOT operation plus pi by 2 phase rotation. So it have additional capacity when compared to X gate. So please take a note. So this is where you can see advantage in quantum. This is where you can see advantage in quantum. So now what I am doing, I am in stage 0. I am applying Y gate. Okay. If I click Y gate, what happens? It will do NOT operation. It will do NOT operation. Okay. So this is similar to NOT gate, no doubt. But if you look downside, you can see phase difference. You can see phase difference. Phase difference is pi by 2. So this is NOT gate plus pi by 2 phase rotation. So this is NOT gate plus pi by 2 phase rotation. So what you got? Your output is state 1, okay, plus pi by 2 phase rotation. So this will give additional computation capacity when compared to classical NOT gate. So like this, you need to understand all this logic. Okay, you are in state 1 plus pi by 2. This is your quantum state. From here, if you are applying Y gate, it will go for state 0. So applying 2X gate next to next will cancel each other. Applying 2Y gate next to next will cancel each other. So X gate, Y gate, Z gate, Hadamat gate have own inverse. So it is like if you are applying X for first time, it will yield 5. If you are applying X for second time, it will yield minus 5. Okay. So what is the net result? It will lead to 0, which will nullify. So imagine in this way. Imagine in this way. Okay. So next we will cover Z gate. Next we will cover Z gate. From stage 0, if you apply Z gate, it will retain the same state. So Z gate will act like identity gate. Z gate will act like identity gate. So click 0, all of you click 0. So click Z and observe what happens, nothing. So Z gate will act like identity only in stage 0. So mention this. So only in stage 0. So click state 1. All of you click state 1. Apply Z gate. It will go for minus state 1. Minus state 1. So observe over here. So click 1. Click state 1. Apply Z gate. So downside you can see the difference. From 0, it will move to pi. It means from positive to negative side. So this is the sign change. So Z gate will act like phase flip gate. Phase flip gate. So what is the value? Pi rotations. So note down. Okay. From minus 1. if you apply Z gate, it will go to positive 1. Okay. So I'll erase this. So now you can able to see. Now you able to see. Now we are in minus state, pi difference, right? Pi phase difference. From here, if I applying Z gate, what happens? It will come to 0. It means it created pi rotations again. So that is what it means. From 1, if you apply Z, it will go to minus 1. So physically, you cannot see any change in your block sphere. But downside, in phase, you can see the difference. So next one is Hadamard gate. Next one is Hadamard gate. Next one is Hadamard gate. Okay. From stage 0, if you apply Hadamard, so all of you click stage 0. All of you click stage 0. Apply Hadamard gate. Observe what happens. It will create equal superposition. It will go to equator. It will go to equator. So it means it will go to positive state. From positive state, if you apply Hadamard, again it will go back to stage 0. So apply Hadamard from positive. Observe what happens. It will go back to stage 0. So from here, again it will go back to stage 0. So if you want to create equal superposition, you need to apply Hadamard gate. So note down. If you want to apply equal superposition, you need to apply Hadamard gate. Okay. So this is one part of Hadamard gate. So from state 1, if you apply Hadamard gate, it will go back to state minus. So all of you click state 1. All of you click state 1. Apply Hadamard. Observe what happens. So it will move from state 1 to negative state. Okay. From negative state, if you apply Hadamard, it will come to state 1. So understanding these gate operations are very important in order to understand composer. So that is why I'm going little slowly. Okay. So all of you click 0. All of you click 0. Apply Z gate, you cannot see any change. Apply S gate, you cannot see any change. Apply S dagger. So this gate is called S dagger. So note down. So this is called dagger symbol. Apply T gate, you cannot see any change. Apply T dagger, you cannot see any change. So what you can conclude, Z gate, S dagger, T dagger, T gate, all are phase gates. Phase gates. Okay. So these phase gates will not operate in stage 0. Apart from stage 0, anywhere in your Q sphere, all these gates will get activated. So note down this point. So Z gate, S dagger, T gate, T dagger, all are related to phase gates. Okay. To understand phase gates, we need to apply Hadamard gate. Now it is in equal superposition. So what we did, from 0, we applied Hadamard gate, it will went to positive state. It went to positive state. So I'll refresh. So give me a second. So we'll continue. So pen is not working. Let me check. Yeah, working now. Okay. So from stage 0, if you apply Hadamard, it will go to positive state. Okay. From positive state, if you apply S gate, it will go to I axis. Sorry, I state, Y axis. So observe, we are in stage 0. I am applying Hadamard gate, it will come to positive. From positive, if I apply S gate, it will go to Y axis. Y axis is nothing but state I. Y-axis is nothing but state I. So what it is doing, it will create pi by 2 phase difference. So Z gate introduce pi, S gate will introduce pi by 2. Okay, T gate will introduce pi by 4. So note down all these steps. So this will help you to understand gate operation. Okay. So from state I, again if you are applying S gate, what happens? Where it will go? It will go for minus state. It will go for minus state. So look at here. I'm applying S gate from I. It will go for minus state. So this is not like previous gates. So this is totally different from X, Y, Z and Hadamard. Okay, if you apply it twice, it will not come back. It doesn't have own inverse. That is why we are creating inverse by using S dagger. Okay, so S gate doesn't have own inverse. T gate doesn't have own inverse. So does not have own inverse we are creating with the help of dagger. So whatever S gate will do, S dagger will do in opposite direction. Okay, will do opposite direction. Okay, so we'll go through T gate quickly, then we will go for composer. All of you click stage 0, click Hadamard. Okay, click T gate. So T gate, what it will do, from 0, apply Hadamard, it will go to positive state. From positive, if you apply T, it will go in between positive state and I state. It will go in between. So try to compare T gate and S gate. T gate and S gate. Okay, 2 T gate equal to 1 S gate. So this is the equation. Note down. 2 T gate equal to 1 S gate. Okay, so compare S gate with Z gate. 2 S gate equal to 1 Z gate. So you can form a correlation like 1 Z gate equal to 2 S gate equal to 4 T gate. So you need to know how we can relate all these gates. So where you need to elaborate, where you need to cut short. Suppose if you want to increase your quantum gates, you can choose appropriately. So all these basics will make you strong to understand quantum gate operation. Now go for composer. So one more time, I will share this link with you. So without login, you able to access this link. So I'll refresh. So all of you able to get this view. So this is integrated platform, SDK. So it contains gate operations. It contains quantum circuit view. It contains coding part. It contains probability. It contains probability. It contains state vector. It contains Q sphere. So these contain 4 quantum bits, qubits. Okay, 4 classical bits. So whatever you observe Q, it is related to quantum. Whatever you observe C, it is related to classical. So for easier understanding what we are doing, we try to click Q0, select bin button, try to select Q0, click Q0, select bin button, Q0, select bin button, keep only one quantum bit. Same way do for C4, click C4, select minus, click C3, select minus, click C2, select minus. So keep only one quantum bit, one classical bit. Are you able to do so? Please put in chat box. So without login also you are able to use. Okay, very good, very good. Give me a second. Okay. So look at here. Your quantum circuit is empty. It means it is always started from zero. So by default, IBM Quantum Composer, IBM Quantum Composer, starting from stage zero. So note down this point. So that is why it is pointing to North Pole. Okay. So look at the probability showing 100% probability for stage zero. Okay. Showing full signal strength for stage zero amplitude. I hope all of you able to recognize this. So right side, you can see open quasim. So if you click Qiskit, okay, you can see. So different code is stored over here. So Open Quasim stands for Open Quantum Assembly Language. So if you got this code, you can convert into Google platform, you can convert into Microsoft, you can convert into AWS. Okay. So we'll cover the first gate, what we discussed. So what is the first gate? We discussed NOT gate. So the second gate is called NOT gate. So drag and drop this NOT gate in your Q0. So state 0, we applied NOT gate. We got state 1. So power supply will happen. power supply will happen. So what you can do, you can use your mouse over here and you can see information. So this is called phase disk. This is called phase disk. Okay. So initially it is in gray color. Now it is turned into blue color. So place your mouse over here. It will give information. So phase equal to 0, real particle to 0, imaginary particle to 0. Probability of state 1 is 100%. Look at your Q sphere. It is located to South Pole. Okay. So look at your probability pointing to 1, 100%. Look at your state vector pointing to 1, full amplitude. So check your code, Quiz-Kit. So you can resize your window in this way. Okay. So circuit is your variable name. So you are implementing X gate in Q0. So coding is self-explanatory. You're able to understand this code very easy. So whatever you do in your quantum circuit, it will reflect. So I'm selecting this NOT gate. I'm deleting. So line number 8 is get deleted. So drag and drop NOT gate. Again, you can see this code. So you can understand the basic code by using this composer. So composer for beginners. Okay, if you want to understand quantum, if you want to understand quantum gates, a basic level circuit, it will help you. But if you go further, if you go deeper, you need to have a dedicated coding platform like a Jupyter Notebook, right? A Google Colab, right? You can use all these tools. So select this gate, press delete button. You look at this information, it looked like gray color. So state 0, probability of state 1 is 0%, which is opposite for state 1. So drag and drop NOT gate. You try to observe the output. Probability of state 1 is now 100%. Okay, if state vector is not found, I will tell you where to look. So go to view, go to panels. Okay, you can have graphic editor, code editor, state vector, probability, key sphere. Okay, so enable and disable these. You can understand how your framework look like. So what I did, I enabled only graphical editor. So one by one I will do. I will enable Q sphere. Okay, I will enable probability. I will enable state vector. I will enable code editor. So I can resize this window, up to you. You can resize. So this is the definition of NOT gate. Okay, definition of NOT gate. So drag and drop one more NOT gate. Drag and drop one more NOT gate. So if you are implementing two NOT gate, what happened? You are starting from stage 0. You applied NOT gate. You applied NOT gate. Okay. So after this NOT gate, it will become state 1. It means power supply will happen. Okay. Again, if you're implementing second NOT gate, so NOT gate 2, again it is converted into stage 0. So stage 0 consider like off state. Okay. State 1 consider like on state. On state means power supply will happen in this wire. Off state means will not happen. So applying two NOT gate will cancel each other, will go back to original state. So we discussed in black sphere, right? So try to recall. Try to recall. Okay. So next what you do, try to implement I gate. So I gate is equal for identity gate. I try to explain. First, we focus on single qubit. It is easy for us. So wait for some time. Can we take 5 minutes break? Can we take 5 minutes break?
Yes, sir.
Okay, sir. Thank you.
Participants, please fill the feedback form of session 5.
Hello, can we start?
Yes, sir.
Okay, thank you. Okay. So let us check. If you implement I gate, it means it is identity gate. It is identity gate. Okay. We are starting from stage 0. If you implement identity gate, the same state retain as it is. So that is why the same state retain. So this is the first example we covered in block sphere. If you apply d equal to 0, it will retain in the same state. Okay. So n number of identity gate, if you are applying, it will do nothing. So it will act like a pass operation. It will act like a pass operation. So drag and drop not gate before this. Drag and drop not gate before this. Okay. So what will you get? You are starting from stage 0. This is not gate. After this not gate, you'll get state 1. Okay. So identity gate you are applying. So state 1 will retain as it is. State 1 will retain as it is. So next, try to implement T gate. All of you try to implement T gate and tell me what is happening. Otherwise, what you do, you can drag and drop Z gate and tell me what is happening. Put in the chat box. So we are applying from stage 0. We are applying Z gate. What you'll get after this? What will you get after this? So don't look at the graph. Okay. Look at your previous node. So try to recall about Z gate. Z gate will not work on stage 0. Very good. So Z gate will not work on stage 0. To do some operation, you need to drag and drop NOT gate. Drag and drop NOT gate. Okay. So we started from stage 0. We implemented NOT gate. So what happened? It will turn into state 1. From state 1, if you apply Z gate, it will go to minus state 1. This minus is indicated with this color wheel. So look at here. So pi stands for this red color. Pi stands for this red color. Okay. 0 means navy blue. So this is navy blue. So in state vector, you will have all these difference. In probability, you don't have difference. So this is related to binary. This is related to binary. This is related to quantum state. So in quantum state only, you have positive, negative, and phase difference. This phase difference is shown in IBM Composer with the help of color wheels. I hope everybody able to follow. So click over here. Sorry, place your mouse over here. Mouse over here. You can see all these details. Okay. So place your mouse over here. State 1, amplitude equal to 1, phase angle equal to pi. Are you able to get this detail? So that is why it is shown in red color. If you click Z gate, if you press delete, okay, it will remove that phase shift. Now phase angle is 0. Okay, so implement Z gate one more time. 2 Z gate will cancel each other. So from state 1, it will go for -1. Again, if you are applying Z gate, it will go back to state 1. So this is how you need to understand quantum circuit. Okay, so if you have so many gates, 50 gates, 100 gates, so how to check your circuit? You need to enable this inspect button. So if you click inspect button, so it will highlight. If you click inspect button, you can see layer by layer visualization. Layer by layer visualization. So all of us starting from stage 0, that is why it is pointing to stage 0. Okay, if we click next, it will implement state 1. If you click next, it will implement Z gate, okay, negative state, -1. Again, if you click one more Z gate, it will nullify each other. So likewise, layer by layer, you can understand if you enable inspect. During inspect, you cannot modify your circuit. So note down this point. If you enable inspect, you cannot modify your circuit. So disable this. Again, delete all these gates. Okay, suppose if you have doubt about any gate, so click that gate, you'll get gate information. So right click that gate, you'll get a simple definition, and you will have Qiskit API reference, and you will have a meaning for open quasing. So I'm clicking that API reference. It will show XGate. It will show all this library matrix. So this is the matrix of NOT gate. Okay, you can see the components in anti-diagonal wise. Okay, so what is the gate for I? 1001. Okay, so X and I are opposite in nature. Opposite in nature. Then they gave a sample notes for this. So you can run all these commands. So in future, if you are using Google Colab, you can go for in-depth coding. So this is how you need to know about all these gates. Okay. So we demonstrated NOT gate, we demonstrated I gate, T gate, S gate. Okay. So click NOT gate, drag and drop S gate. So what S gate will do? S gate will implement pi by 2 rotation. So look at this pink color, pi by 2. Okay. So if you drag and drop one more S gate, it will act like Z gate. So pi rotations. So delete this S gate, drag and drop T gate. So it will go for in between pi and pi by 2. So it will go here. So it is the mixture of pink and red. Okay. So if you apply one more T gate, the whole combination related to one Z gate. Okay. So 2 T gate equal to 1 S gate. So it will look like 2 S gate. It will look like 2 S gate equal to 1 Z gate. So likewise, what is supposed to do? Drag and drop each and every gate. try to understand how it is working. So you need to know its principle, you need to know the visualization, then you need to know the color code, what it represents. Okay. So what you can do, you can enable face angle in QSphere. So enable this. So it will show the face angle. So we'll resize this window. If you place mouse over here, it will show face angle. So select all these gates. Select all these gates. Delete. Delete. So we covered single qubit gates. We covered single qubit gate. Okay. Now what we going to do? We're going to implement Hadamard gate. So this is actual quantum gate. It will create randomness. So what Hadamard gate will do? It will create equal superposition. It will create equal superposition. So sometimes it will generate state 0. So we are starting from state 0. So sometimes it will create state 0 as the output. Sometimes it will create state 1 as the output. So two possibilities are there. Okay. So these two possibility, it is showing simultaneously. So if you place over here, you can see two possibility, 50-50 chance. So slight difference will be there. You can see over here. So 0.50001, if you move to state 1, so 0.49, 0.4999. Little difference are there, not exactly 50-50, little difference will be there. Okay. Now what we going to do? We try to do measurement. We try to do measurement. When you do measurement, superposition state will get collapse. Okay. You have two possibility, right? Out of two, we'll get only one possibility. So all of you do this. All of you do this. Okay. So click drag and drop Hadamard gate. Okay. Followed by this measurement gate. You can see a measurement gate like this. Drag and drop. So this will convert your quantum information into binary form. So you cannot retain quantum state. It need to be converted into binary form. So finally, in your computation, you'll get binary value. So this is what it means. So once you click this measurement, if you press delete, again you can see superposition. Again you can see superposition. So look at your amplitude. Here there is an interesting twist. For 1, it represents 0.707. For 0, amplitude 0.707. So look at the probability, 50% for state 1, 50% for state 0. So do measurement gate. Do measurement gate. Superposition state will get collapsed. You will have only one possible outcome. So this is, you need to know how superposition act when you do measurement. So any doubt within this, you can ask me. So all these gates are clear. All these gates are clear. Yeah, phase angle is always 0 because we are not implemented any phase difference. So we are only concentrating on state 0 and state 1. If you do measurement, it doesn't matter whether it is pointing to -1 or +1. You will get 1 only, binary value 1 only. Are you able to get the idea? Okay, implement. I will give 1 minute time. Play with your gates. Implement Hadamard followed by measurement gate. So look at here, half circle, half filled with gray color, half filled with blue color. So probability of state one is 50%. So all of you able to understand this until this? So any doubts you can ask me, because we are going for 2-level qubit system. Yeah, we can go. So select this Hadamard gate, press delete. We need to increase number of qubit. So click Q0, select plus, resize your window, click C1, click plus. So difference is, if you have multiple qubits, you can visualize individually. But if you have multiple classical bits, you can see in combined double line view. Okay, so this is the primary difference. If you click Q1, if you click press, you have 3 qubits. You can see individually. But classical, you can see only double line. So primary difference. So note down this. Note down this. Now we about to cover control NOT gate. So control NOT gate is very important, right? So we'll cover some theory for control NOT. Okay, this is about control NOT. So in short form, they call C NOT gate. So write down this definition. Control NOT gate, C NOT gate acts on 2 qubits. So C NOT gate, if you want to implement C NOT gate, at least you need 2 qubits. Okay, flips the second qubit if the first qubit is 1. So this is the basic rule. So it is a conditional NOT gate. So you can term in different ways. So control NOT gate, C NOT gate, or conditional NOT gate. So you have quantum circuit, you have 2 qubits, Q1 and Q2. Okay. So the first one is control, the second one is target. So you can imagine control is acting like a switch. Control is acting like a switch. Okay. So this NOT gate will act like appliance. Any appliance, it could be light, it could be fan, it could be anything. Imagine in such a way. Okay. If there is a power supply, if there is a power supply in Q1, okay, because of soldering, it will come down. Power supply will come down. If power supply come down, this NOT gate is activated. This NOT gate is activated. Okay. If it is activated, it will do bit flip for Q2. Otherwise, it won't do anything. So this is the logic of control NOT gate. So after your control NOT, your quantum state will get changed in Q1 dash and Q2 dash. Okay. So this is the truth table. So we are taking the first scenario, stage 0 for Q1, stage 0 for Q1. Okay. State 0 for Q2. I will change different colors so you can understand easily. I will take 0 for Q2, state 0 for Q2. Okay. There is no control. There is no signal in control in Q1. So Q1 acting like a control. Okay. Q1 acting like a control. Q2 acting like a target. Okay. So what is the definition? If first qubit is 1, if first qubit is 1, it will flip second qubit. Okay. So notice this condition. Q1 is already 0. So it won't do anything for Q2. So in combined state, we'll get 0, 0. So combined state, you'll get 0, 0. Okay. So next what we'll do, we are implementing Q0 equal to 0. Sorry, Q1 equal to 0. So we are starting with 0. Q2 with 1. So Q2 with 1. Okay. So according to the definition, there is no control, no signal in the control. It means no power supply. This NOT gate is inactive. So whatever the state for Q2, it will retain as it is. So combined state, what you got? Combined state, what you got? 0, 1 state. So Q2 retained as it is. So next, look at the input. Q1 is 1. So Q1 is 1. Okay. So Q2 is 0. It means there is control in Q1. If there is control in Q1, Q2 will get negotiated. It is converted into 1. Are you able to see the difference? So combined state is 1, 1. Okay. So look at the last combination. Q1 is state 1. Okay. Q2 is state 1. Okay. So power supply is there. Control is there. It will come down. It will enable your NOT gate in second qubit. So it will do bit flip. So it will convert into state 0. So if there is a control in Q1, in this case, okay, in this case, Q2 is negotiated. Q2 is negotiated. So this is the crux of control NOT gate. So remaining, it will retain as it is. It will retain as it is. So it will retain as it is. So here you can notice like this is Q1 and this is Q2. So technically you can say Q1 dash and Q2 dash. So all of you able to understand this? Can we proceed? If you have any doubt, you can ask me. Okay. So we'll go to implementation. If you're able to understand this. So this is control NOT gate. So what is the value we had? We had stage 0 initially. Okay. So stage 0 means no power supply. So it will not come down. So NOT gate is inactive. You'll get stage 0 as it is. So in Q0 also stage 0, Q1 also stage 0. So combined state is state 0, 0. So this is the first example. This is the first example. Okay. To enable control NOT, what we are doing, we are implementing a NOT gate before that. We are implementing a NOT gate before that. So state 0, we have NOT gate. So it is turned into state 1. State 1 means power supply will be there. It will come down. This will enable this NOT gate. So here also state 0. Now it is converted into state 1. So this wire also have power supply. This wire also have power supply. So combined way, you can say state 1, 1. Now it is pointing to south pole. Okay, previously it is pointed to north pole. So if you have 2 qubits, we have 4 possibility: 0, 0, 0, 1, 1, 0, 1, 1. So try to explore all these possibility. Try to explore all these possibility. So empty circuit will lead to 0, 0. Empty circuit will lead to 0, 0. If we implement not getting Q1, what happens? If you implement not getting Q1, so state 0, implemented not gate leading to state 1. Okay, so downside state 0. So what is the combined form? 0, 1, 0, 1. So in Qiskit, they have some reverse mapping. So Q0 map to rightmost bit. Okay, so Q1 map to leftmost bit. So note down this reference. So the topmost qubit map to rightmost bit string. Okay, the lowest qubit map to leftmost bit string. Next, what you do? You drag and drop this NOT gate for Q1. Now it is shifted for 1, 0. Now it is shifted for 1, 0. Okay. Drag and drop one more NOT gate. Now you got state 1, 1. Now you got state 1, 1. So sometimes if you need to feed your input, you need to know how to feed your input. 0, 0, 0, 1 or 1, 0 or 1, 1. By using NOT gate, you're able to achieve these states. Okay. So next what we'll do, we try to implement Hadamard gate in Q0. We try to implement Hadamard gate in Q0. Okay. So try to recall from previous. We starting from 0, 0 state always. So Hadamard will produce state 0 and also it able to produce state 1. Okay. So for Q0, you have two combinations, two possibility. For Q1, you have only one possibility. So always state 1 create state 0. So look at the first combination, state 0, 0. So this 0 is possible by Q0. Okay. This 0 is possible by Q1. So that is why you got 0, 0 states. So look at the next combination. Look at the next combination, 0, 1. Okay. So this one is possible by Q0. This 0 is possible by Q1. So that is why 0, 1 is possible. So look at the third combination. What is your third combination? 1, 0. Okay. So this 0 is possible by Q0, but this one is impossible by Q1 because Q1 always produce state 0. So that is why you are not able to get this state. Simultaneously, you are not able to get 1, 1. So if you know this mapping, you're able to understand how your output works. So any doubt within this, you can ask me. If you are not clear, I will retake one more time. Yeah, I will tell. Okay, I will repeat this portion. I will repeat this portion because this is very important. I will erase all this stuff. Maybe I will go for whiteboard. So we have 2 qubits. So Q0, Q1. Okay, we implemented Hadamard gate in Q0. So what is the possibility of Q0? It will create state 0. It will create state 1. So all these qubit initialized in state 0 initially. Okay, so there are 2 possibility for Q0. So state 0 and state 1. Okay, so what is the possibility for Q1? Only 1. So always state 0. Okay, so take first example 0, 0. This state. Okay, so this 0 is possible by Q0. This 0 is possible by Q1. So this is the format of Q1 and Q0. So note down in this way. Then you will get clarity. Okay, so look at the second possibility. 0, 1. 0, 1. Okay, so I'll try to change color. Okay, color here we can change. Okay, so this one is possible by Q0. This 0 is possible by Q1. So this is possible. So look at the third combination. Okay, 1, 0. 1, 0. I try to change color. So this 0 is possible by Q0. Okay, so this one is impossible by Q1 because Q1 always produce 0. That is why this whole combination is eliminated. In the same way, you can eliminate 1, 1 because it is not possible by Q1. Is it clear now? So why we got 0, 0, 0, 1 for this circuit? Only 2 states are possible, not 3. So check with this circuit. So combination, right? You need to combine Q0 and Q1. Okay. So drag and drop Hadamard gate in Q1. Now observe your circuit. Drag and drop Hadamard gate to Q1. Now you're able to get 0, 0 and 1, 0. You are not able to get 0, 1 and 1, 1. So work out with pen and paper. It will be easy for you. Work out with pen and paper. So like this, you try to do for this one. So Q0, Q1. So you need to do for Hadamard gate in Q1. So 0, 0 state is possible, right? And 1, 0 state is possible. So we have 2 possibility for Q1. So state 0 always for Q0 in this case. So drag and drop Hadamard gate in Q0. Now look at your output. So you have two superposition. So one superposition created in Q0, one superposition created in Q1. So you have all possible combination of two qubits, 0 0 0 1 1 0 1 1 simultaneously. So you'll have equal amplitude, so you'll have equal probability. So place over your amplitude 0.5, place over your probability 25%. So four state means equally distributed. So like normal probability, right? Equal probability, equal distribution. So I'm deleting Hadamard gate. I'm deleting Hadamard gate in Q1. I'm implementing a control NOT gate. I'm implementing control NOT gate. Now what is happening? So you already know control NOT, how it works. You already know how Hadamard gate works. Look at your output. Look at your output. You got state 0, 0 and state 1, 1. What is the meaning of this? Put in the chat box. So 1, 2 means, oh, what is the meaning of 1, 2? Can anybody able to tell what is the circuit will do? Have they covered entanglement in previous session? So this is an example for entanglement. So if you want to recall, I will take that portion. So entanglement is strong correlation between two quantum particle. So okay. So under the right condition, you can take two electrons or two photons. You can create strong correlation between them. That is called entanglement. So once you do in laboratory, then you are able to separate those quantum particles. So one particle you kept at Earth, one quantum particle you kept at other place in this universe. Okay. So even though if you separated entangled quantum particle, all these properties are strongly related. So whatever happens for one quantum particle, it will affect the other quantum particle. Okay. So if you want to understand, you can compare with rock, paper, scissors game. So if three persons are playing rock, paper, scissors, so measuring one instantly decides the state of other player faster than the speed of light, theoretically. So it is very easy to decide who won that match, who lost that match instantly. Okay. So entanglement will happen instantly, irrespective of distance between them. Okay. Quicker communication when compared to classical communication, instant communication. So it will influence each other state even if they are galaxies apart. So theoretically, it is the conclusion we are having. Okay. So we have two quantum particles. So we have two quantum particles. This is photon 1, this is photon 2. If you are creating strong entanglement in lab, then what you are doing, you are separating this quantum particle. You kept it one particle in Earth, one particle in satellite. Imagine in such a way. Okay. So this quantum particle can rotate in upside or downside. If it is rotating upside, it is state 0, downside state 1. Okay. Imagine if your quantum particle moving to downside, moving to downside. It means it is representing state 1. It is representing state 1. So instantly what happened? The other quantum particle also match the same state. So it will also go to downside. Okay. So if you are doing anything in your quantum particle 2, if you are rotating to upside, so imagine this P1 also moving to upside. So whatever happens for one quantum particle, you can see the same effect in particle 2 if it is entangled. So this is the meaning of entanglement. Now come to the circuit. Come to the circuit. So look at the two case. So one possibility, it will create state 0. So if it creates state 0, Q0 will generate state 0. Okay. Q1 also generates state 0. So both are correlated. Okay. Suppose if Q0 creating state 1, Q0 generating state 1. Okay. So Q1 also generate state 1. So equally correlated, positively correlated. So that is why the first quantum particle is 0, the second quantum particle also 0, the first quantum particle is 1, the second quantum particle is 1. You got two combination, either 0, 0 or 1, 1. So here it is in both combination because in superposition. So we created superposition and we created correlation between Q0 and Q1. So I try to explain with separate code if it is difficult for you. So this is our circuit. So we have Hadamard gate. Okay, we have Hadamard gate. So Q0 and we have Q1. So we have control knot. We have control knot. Okay. So two case. Case one. If Hadamard gate produce state 0. Case 2. If Hadamard gate produce state 1. Okay. I try to copy the circuit. Okay. So two cases we have. Okay. So we are starting from stage 0. Okay. If Hadamard gate produce stage 0, it means no power supply. Okay. No power supply over here. So stage 0 retained as stage 0. So here also 0, here also 0. In combined form, you will get 0, 0 state. Okay. So here it will create state 1. Imagine if your Hadamard gate produce state 1. So power supply will be there. It will come down. So this NOT gate is activated. This state 0 is converted into state 1. So here also power supply will happen. In combined view, you have state 1, 1. So this is how you got. All of you able to understand? Okay, great, great. So this is very important circuit. So this is called Bell states. So we have four different kinds of Bell states. We have four different kind of Bell states. Okay. So we try to do with not gate, with not gate. So all of you do this. All of you do this. What is the output you got? So implement not gate before this control not and tell me your answer. Put in the chat box. So do pen and paper work. Easily you can able to understand what is happening. Exactly. So it will create 0, 1, 1, 0. What it means? Can anybody able to figure out why it creates 0, 1 and 1, 0? What is the meaning of it? For this scenario, you're talking outcome probability. No. Look at the outcome probability mentioned over here. So 50% for 0, 1, 50% for 1, 0. Exactly. So it will do opposite of control not gate. So what it means, whenever there is a power supply, okay, it will not do not operation. It will not do not operation. So it is opposite entanglement. So note down, it is opposite correlation. So like 0, 0, 1, 1, we can create 0, 1 and 1, 0. Yes, great, great. Fine. So likewise, I'm deleting this NOT gate. I'm implementing Z gate and tell me what is happening. So do the circuit, work out in pen and paper, and tell me the reason. All of you able to follow, able to do? Okay. So try to answer this question. If you're not able to understand, let me know. Exactly 0011, but what is the difference over here? Yes, phase angle for state 1. Okay. The phase angle is added pi rotations. Okay. So this is very important concept in quantum. Okay. The simple experiment demonstration got Nobel Prize. So don't think Nobel Prize always need to be very difficult. Okay. So this experiment cracked 60 years mystery in quantum. I try to look at that slide. Bill states. So we try to recall, refresh, entanglement. So if you have two quantum particles, if you are correlating equally, you will have positive correlation. If you measure, you'll get the same state like friends. Okay. But if you are creating an entanglement oppositely, okay, it will create opposite states instantly. It will create opposite states instantly. To understand this, we need to understand this entanglement circuit. Okay, so this is the initial state 00. We are applying Hadamard gate. Then this initial state turn into 1 over 2 state 0 plus 1 over 2 state 1. So what I do, I try to draw this scenario. So this is the combined state. So this is step 1. Okay. So if you implement Hadamard gate, this is step 2. You get this equation over this point. Okay. So this is equal to positive state. So recall from stage 0, if you apply Hadamard, it will go to positive state. So positive state you can represent in this way. Positive state you can represent in this way. Okay. So if we combine these two states, this is 3. Okay, we are multiplying the whole positive state with state 0. So this is the combined state. Okay, so next what you are doing, you are implementing control knot. So if you implement control knot, you know what will happen. Whenever there is a control, it will alter the second qubit. It will alter the second qubit. Okay, so that is why you got 00 and 11. Okay, so the whole form belongs to step number 3. If we add control knot over here, this is the final combined state. This is the final combined state. Is it clear? If you have any doubt, you can ask me. So this notation you can give in multiple forms. This notation you can give in multiple forms. So 1 over root 2, we discussed 1, 1, right? So this is one more notation. If you multiply 1 over root 2, so like this, 1 over root 2, 1 over root 2, in this way. So multiple way to represent past history. So is it clear? Shall we go to next slide? Put in the chat box.
Yes, sir.
Okay, thank you, thank you. If you want to study quantum, you need to understand very slowly, very gradually. If you have any doubt in between, you cannot proceed. So after some point of time, it seems so difficult. So always starting from basic gates, try to understand mathematically, try to implement circuit wise, do visualization as much as possible, as frequently as possible. Okay. Suppose if you're implementing the equal correlation like the previous gate, you'll get 0, 0, 1, 1. Okay. If you are creating a opposite correlation, adding NOT gate before control NOT, okay, you'll get this gate. So I'll draw this circuit over here. So how we achieved? We implemented Hadamard gate. We implemented Hadamard gate. Then we implemented control NOT. Okay, to achieve this state. So how we achieve this state? We have Hadamard gate. Okay, we have control NOT gate. And we implemented NOT gate before this. Okay. Then we got this state. How we got this state? We have Hadamard gate followed by control NOT. Okay. And followed by Z gate. So this will do phase flip. This will do phase flip. So can see correlation between these two circuits. Only Z gate is added after control NOT. Okay. So if you want to achieve this one, what is supposed to do? So you need to recreate the same circuit, Hadamard gate, followed by control NOT. Okay. So before that, you need to add NOT gate. So after this, you need to add Z gate. So if you introduce Z gate, it will introduce a phase shift, a sign change. So for this experimentation, for this demonstration, they awarded Nobel Prize. They awarded Nobel Prize. So scientists not able to solve this mystery for 60 years, including Einstein. Okay, so this is called Bell states. So you can take notes. This is called Bell states. There are 4 possible states of entanglement. So this is the implication. This is the implication. The probability of first qubit is 0 is 50%. Then the probability of second qubit is 0, 100%. Okay, so this is the basic about IBM Qiskit Composer. There are a lot of gates are there. If time permits, we will cover 1 or 2 gates. Okay, so try to implement this fab gate. Try to implement this fab gate. So what is the state before this? Stage 0, stage 0. Okay, swap gate what it will do? I will change with color. I'll change with color. So this is the state 0. Okay, so this state 0 is transferred to q0. Okay, so this state 0 is transferred to q1. So this is the operation of swap gate. So like classical swap, it will do quantum state swap. Because both qubits are in same state, we cannot see output difference. Okay. So how we are able to differentiate quantum states using swap gate? Can you give any idea how to visualize swapping? Put in chat box. Exactly. Exactly, ma'am. So we need to implement NOT gate over here. NOT gate over here. So let me discuss. We started from stage 0. We started from stage 0. So we implemented NOT gate. We implemented NOT gate. So now it is turned into state 1. Okay. This state 1 is transferred to here. Okay. This 0 is transferred to here. So that is why you have different outputs. That is why you have different outputs. To visualize this, delete this swap gate. You can see the Q0 is blue color, the Q1 is in gray color. But if you do swap, it will automatically change. So during quantum computation, you can transfer your quantum states from one qubit to another qubit by doing this. If you want to retain from some other quantum operation, you can use swapping. Okay. So likewise, you are able to explore all these quantum gates. Okay. So the next one is 3 qubit gate. 3 qubit gate. For this, you need to add control not gate. So this is called control not gate. CC not gate, or you can say control not gate. So initially, what is the state? 0, 0, 0. Okay. 0 means no power supply, no power supply. Okay. So not gate is not activated. You will retain the same state. You will retain the same state. So to understand control not gate, okay, implement a not gate before this. So what it means, we started from stage 0, stage 0, stage 0. We implemented not gate. So after this, power supply will be there. So it becomes state 1. Okay. But the second qubit is not given with power supply. So two switches are there. Two switches are there, which is in serial form. So this is switch 1, this is switch 1. Okay, if NOT gate need to be activated, both should work like AND logic. So this should be on, this should be on. Otherwise, you cannot get power supply for your NOT gate. Okay, so what happened? What happened? Switch 1 is on, switch 1 is on, switch 2 is off state. So what is the logic? AND operation between S1 and S2. So that is why you got state 1, state 0, okay, state 0. So here two controls. If you understand control not gate, so simply extend that concept. Two controls are there. So to enable this, implement one more not gate. Implement one more not gate. Okay, you have two not gate. It means you have state one, state one. Okay, so power supplies are there. So both switches are in on state. Both switches in on state. So power supply will come down. This NOT gate is activated. So state 0 turn into state 1. So Q2 will do NOT operation if both qubits are in state 1. Then only it will get bit flipped. Then only it will get bit flipped. Are you able to see now? So here state 1, here state 1, here state 1. So combined form, you have 111 state. So you can go all this menu. You can view circuit view customization. You can enable code editor. You can download this file. Okay. So you can do all this stuff. You can go for documentation also. So here they will give a detailed explanation about composer. Okay. So you can go for this. I'll share this link to you. So you can do self-study. So it will take some time. It will take some time to understand all this stuff. So don't worry about that. Go slowly, gradually. Okay, they will give very detailed explanation. So you can run this circuit. Take an example of Hadamard gate. Okay. So until this, we saw only the simulation. If you want to execute in real environment, real quantum computer, so you need to have your login. So without login, you cannot access real quantum system. You need to go for setup and run. So for me, it will show in this way. Okay. So I need to select the available quantum processor. So QPA means quantum processing unit. So these three quantum systems are available for me. So it should be available for me. So IBM Torino I am selecting. Okay. Then I'm clicking run circuit. So I'm running this circuit for 1024 times. Okay. But it's showing error because you cannot implement Hadamard gate. You need to do measurement. You need to do measurement. Okay. So I'm running this circuit for 1024 times in IBM Torino. I'm submitting this job to real quantum system. So my job is sent to the quantum processor and it is in pending. So sometimes it will execute very quickly. Sometimes it will take some delay. So it will take 1 hour, 2 hour, some days, half day, 2 or 3 days, depends upon the queue and priority. What is the processing speed or measurement? So measurement will convert your quantum state into classical form, binary form. That's all. Binary bits. Normally, it will execute within milliseconds or microseconds. We need to export. That is what I told. So go for circuits. Go for circuits. You are able to duplicate. You are able to export circuit image. You can save file. Okay. You can do all this stuff. So I already submitted so many jobs. Completed. Now it is completed. So it took only 2 seconds, including the queue and completion. So this is the output of Hadamard gate. Okay. So we got 1 for 467 times. We got 0 as the output for 557 times. If we add together, it will go for 1024 times. Okay. So this is how we able to understand IBM Qiskit Composer. So in future, if you want to know information about quantum, so you can follow my LinkedIn page. So this is my social media ID. I'll share this link to you. You can give connection request or you can follow. So in future, I'll keep on post what is happening inside India or outside India related to quantum domain. So you can use multiple tools. You can use Jupyter Notebook to install Qiskit. You can use Google Colab. Thank you all. Thank you.
Thank you so much, sir. Participants, do we have any questions regarding this? If you have any questions, please do ask. You can directly unmute yourself and ask the questions that you have.
Hello. Hello,
Hello,
sir.
Hello.
hello,
Tell, sir.
sir. Hello,
Yes, sir. Audible. Tell, sir.
sir. I am Anna, a research scholar from Kerala.
Okay, ma'am.
I have started my research 1 month back in quantum optimizations and all.
Okay.
I am
Okay.
a fresher for this area,
Okay.
and I have started a course in Coursera offered by Packet.
Okay.
There, I'm able to find this Q-skit.
Mm-hmm.
Before that, I have gone through that mathematical foundations and all as a specialization course I took. Then last day, I have came across this Q-skit composer, and in that, actually, the course was taken in 2021. It's a recorded thing, and it is entirely different for me when I have run yesterday, 2 days back. Then I have created an account and taken that API token.
Okay.
Then there I have applied using my credit card. Then in that course, it is shown that you can use this API token and run in your Jupyter Notebook or Python Colab. Then I have made this API token and taken that and go for this collab and have executed that thing, and I'm able to run only for some seconds. Then it has shown that there is when I go with the code execute like that way, in order to run on this actual quantum computer, I have selected what are the
Simulator.
available machines. Then I got a list of three, which is similar, which is shown by you today. Then I have to choose the one machine and try to execute my circuit. Simple hardware gate and CNOT gate, simple circuit, but I am not able to execute, and it shows that the account is or your plan is like that way. Uh, am I able to execute it, or my any fees will be added to my account?
Yes, ma'am. You should be very careful when you run this IBM quantum system. Nowadays, they are charging 9,000 rupees per minute. So if
Oh,
you
but
accidentally run, if you're not able to stop that process, they will charge you like anything. So try to use
then I got
simulator
a
as much
mail
as
that
possible. Yes.
my account is deactivated.
Okay.
I then is did I should send any mail to the supporters, or um, I should be stop back or hold back?
You need to email them, ma'am. They will support you. So mention all these reason. They will enable
Okay.
your account.
As
Sometimes
part of the
they
course, I
find it
just
is
started and gone
malicious.
through, but
Sometimes they will find your activity as malicious by software.
okay. So they deactivated my account. Like that way, I got a message.
Okay.
I have given that credit card credentials and all in for creating that API key.
Okay. Okay.
So you in the screen which you have shared, I have also seen that API token, and
Uh-huh.
it is encrypted way.
Yes. Yes. Yes.
Like that way, I got also one. Then I used gone with that course, and I'm still stuck on that uh, way, not able to run like that way. So I asked, surely I will message them. I will send a mail. Uh,
Okay. Okay. Okay.
okay, thank you, sir.
Thank you. Thank you.
Excuse me, sir.
Yes, sir. Tell me, sir.
Yeah, myself Krishnarao from Hyderabad. Uh,
Okay.
Sir, what makes magic state distillation the largest overhead in fault-tolerant quantum computing, sir?
Very difficult question, sir.
Mhm.
We'll start from very basic, sir. You go from
Okay,
basics.
okay,
To get a good grasp, at least you need 6 months or 1 year time period.
okay, sir.
So don't think too much. Start from course one, what I shown from today link. Complete course
Okay,
one, then complete course two, then go for advanced level topic in this way.
okay, okay,
Magic
sir.
state is still hypothetical.
Okay, okay, sir. Thank you.
Thank you, sir. Thank you.
Sir, in real life, any application that we can see real life applications on quantum computing?
Real life right now no applications, but it have potential. So imagine in 1940 how we had normal system in vacuum tubes. In same era we are in quantum. So it will require minimum 15 to 20 years to evolve quantum hardware. Once it is evolved, we can see a real life implementation. So until that, we need to learn this technology. We need to have a theoretical foundation. When hardware evolved, you can expect a real life implementation. So theoretically, it is proven. You have Schwarz algorithm, you can break RSA coding. Okay, theoretically, mathematically, it is proven. But hardware is not evolved. So
Okay,
whatever we do in quantum right now, we do with toy level problem, toy level data sets. Hardware is
okay,
not evolved. That is the problem. You can do n number of applications, sir. You can do DNA sequencing, protein folding, okay, cyber cryptography, post quantum cryptography. You can find new materials. You can do chemical simulation. Everything is possible, but hardware is not about.
Got it, sir.
Okay, sir. Thank you.
I have a small request to make to all the participants. Please open your camera for few minutes to take a screenshot.
Done.
Thank you so much, sir.
Thank you, ma'am. Thank you so much. Thank you all.
Thank you so much, Dr. Jay Kumar, Vidya Shankar, sir, for such an engaging and informative session. Your step-by-step guidance on QSKit and practical demonstration have given us a clear understanding of how to utilize quantum stimulators effectively. This session truly bridged the gap between theoretical knowledge and practical applications. We deeply appreciate your time and effort in providing us with such valuable insights. The knowledge gained today will undoubtedly be a strong foundation for further exploration in quantum programming and simulations. A big thank you to all the participants for your active engagement and enthusiasm throughout the session. Your questions and interactions added great value to this learning experience. Before we wrap up, a gentle reminder to please kindly fill out the feedback form for this session that has been shared in the WhatsApp group and the chat section area also. Your feedback is crucial to us and help us to improve our future sessions. With that, we conclude our session 6. Stay tuned for the upcoming sessions. Thank you so much for being the part of this beautiful journey. Thank you, sir. Thank you to all the participants.